Right now, you are moving faster than a rifle bullet. You don't feel it. You never have. Your coffee doesn't spill. Your feet stay planted on the floor. But if you're standing near the equator, the ground beneath you is spinning at roughly 1,000 miles per hour, carrying you around the planet's axis every single day without so much as a whisper of resistance. What if that stopped? Not slowed down, not gradually eased to a halt over centuries. Stopped completely in one single second. The honest answer is far stranger and far more violent than most people imagine. Here's the part that makes this hard to picture. You are not just standing on the Earth. You are moving with it. Every atom in your body, every drop of water in the oceans, every molecule of air in the sky, all of it is signing together at the same speed, locked in step with the planet beneath it. Physicists have a word for this shared motion: momentum. And momentum does not like to disappear. This idea goes back centuries to the foundational laws of motion laid out by Isaac Newton. Newton's first law states, in essence, that an object in motion stays in motion unless something forces it to stop. You, right now, are that object in motion. The only reason you don't notice it is because everything around you, the air, the ground, the buildings, is moving at exactly the same speed you are. There's no relative difference to feel. Now, imagine the ground beneath you obeys Newton's law and instantly slams to a stop. What happens to you? You don't stop with it. Your body keeps moving at that same 1,000 miles per hour because nothing has acted on you directly to slow you down. The ground has simply vanished out from under your momentum. In practical terms, you would be launched sideways at a speed several times faster than the most powerful hurricane winds ever recorded on Earth. And you would not be alone. The atmosphere itself, all of that air surrounding the planet, would keep moving too, because air is not rigidly bolted to solid ground the way you might assume. The result would be winds strong enough to strip forests bare, flatten buildings, and scour the surface of the planet in a matter of seconds. Not a storm, not a hurricane, something without a real name, because nothing like it has ever actually happened in recorded history. The oceans would behave the same way. Water, unlike solid rock, is a fluid that resists sudden changes in motion even more dramatically. Trillions of tons of ocean water would surge forward, piling into coastlines in walls of water that would make a tsunami look modest by comparison. Entire coastal cities, the ones perched right at sea level, would essentially cease to exist within moments. Why would something so quiet and gradual as the planet's spin cause something this catastrophic if it changed instantly? Because your entire world was built, biologically and structurally, around the assumption that this spin would remain smooth and constant. Nothing on Earth, not your bones, not your buildings, not the ecosystems around you, was ever designed to survive an instant break in that rule. Now, here's where the story becomes genuinely strange rather than just destructive. Earth's rotation is not actually as fixed and eternal as it feels. It changes all the time, just at scales far too small for your senses to register. The geophysicist Richard Gross, working at NASA's Jet Propulsion Laboratory, has spent years studying exactly how much the planet's spin can shift and what causes it. Gross calculated that after the devastating 2011 earthquake in Japan, Earth's rotation actually sped up, shaving roughly 1.8 microseconds off the length of a day. Not seconds, microseconds. A shift so small no human being on the planet could ever feel it, yet precise enough for scientific instruments to measure and confirm. How could an earthquake possibly change how fast the entire planet spins? The same way a spinning ice skater speeds up when they pull their arms inward. When a massive earthquake shifts enormous amounts of rock and mass slightly closer to Earth's core, the planet's distribution of weight changes just enough to alter its rotation, following the exact same physical principle: conservation of angular momentum. Mass moves inward, spin speeds up. Mass moves outward, spin slows down. A similar effect was documented by the researcher Benjamin Fong Chow at NASA's Goddard Space Flight Center following the catastrophic 2004 earthquake near Sumatra. Chow's calculations showed that this single earthquake was powerful enough to measurably shift the planet's rotation and even nudge its axis slightly. A real physical consequence of a natural disaster reaching all the way up into the mechanics of the entire planet. So, if an earthquake, a purely local, contained event, can nudge the whole planet's spin by a fraction of a microsecond, what does that tell you about the scale of energy locked inside Earth's full rotational momentum? It tells you the number is almost incomprehensibly massive, which is exactly why stopping that spin instantly isn't just implausible, it's physically catastrophic on a scale that dwarfs every natural disaster in recorded human history combined. But suppose, purely as a thought experiment, that some impossible force did bring the spin to a halt gradually instead, over months or years rather than one violent second. What then? Even in that gentler version, life on Earth would transform into something almost unrecognizable. A single rotation on its axis is what gives you day and night in a 24-hour cycle. Stop the spin, and one side of the planet faces the sun permanently, baking under endless daylight, while the other side freezes in permanent darkness. Only a narrow band along the border between light and dark, sometimes called a terminator line, would offer temperatures anywhere close to what you experience now. Weather patterns would completely reorganize. The Coriolis effect, the force responsible for the spinning motion of hurricanes and the general circulation of global wind patterns, depends entirely on the planet's rotation. Without it, storms would stop spinning the way they do now, and entire climate systems that took millions of years to stabilize would unravel and rebuild themselves into something new. You would be living, quite literally, on a different planet, even though the ground beneath you never moved an inch. And that's the strange part worth sitting with. You spend your entire life standing on something moving faster than sound, in a system so perfectly balanced that a single instant of disruption would be indistinguishable from the end of the world as you know it. And yet, you feel nothing. No wind in your face, no sense of speed, no warning sign of just how much is quietly, constantly in motion beneath your feet. So the next time your coffee sits still on the table and your footsteps land exactly where you expect them to, remember what that stillness is actually built on. You were never standing on solid, unmoving ground. You were moving faster than a rifle bullet the entire time. And the only reason it never felt that way is because so far, it never had to stop.